Everybody, good afternoon. Let us start with the second session in our workshop today. This is the last section of the workshop. We have 4 presentations, 3 oral communications, and a plenary lecture. Thank you for the audience, for the people that are in the audience. Thank you for the people that are in the far from Brazil. Good evening for them. And ask for excuse because in the session in the morning, we had to make the presentation in Portuguese because the people who hold the presentation could not speak English enough to a presentation. So please, pardon for the communication in Portuguese. Okay, let us start then with the first oral communication this afternoon. This is from Amanda Rodrigues Pinto Costa. Amanda is a graduate student from our program at UF, Universidade Federal Fluminense. She works in the lab of organic chemistry with supervisor Professor Pedro Batalha, and she will speak to us about understanding the emissive behavior of aminoquinolones in the presence of TFA, trifluoroacetic acid, for application in biosensors. Please, Amanda, you can start with your presentation. You are welcome.
Obrigada, professor. Meu nome é Amanda Costa, sou aluna do professor Pedro Neto Batalha e vou apresentar meu trabalho intitulado Understanding the Emissive Behavior of Aminoquinolones in the Presence of TFA for Application Biosensors. Bem, as 4 quinolonas, elas são derivados oxidados do núcleo quinolínico e elas consistem em um heterociclo aromático que podem existir na sua forma tautomérica 4-hidroxiquinolina. E em relação à bioatividade dessas substâncias, inicialmente foi atribuída a atividade antibacteriana para o núcleo quinolônico e ficou conhecida como atividade clássica. Com o passar dos anos, outras atividades foram sendo atribuídas a esse núcleo, podendo se destacar atividade anticâncer, antiviral, antifúngica, antiparasitária e outras. E também é possível encontrar na literatura o núcleo quinolônico sendo associado a propriedades fotofísicas. Nessa primeira substância, nós temos um sensor fluorescente para determinar para determinação de íons ferro e cobre por complexação. E neste último aqui, por exemplo, nós temos um sensor fluorescente para detecção de polióis. Em relação às aminoquinolonas, elas são substâncias que possuem grupo amino em qualquer posição do núcleo quinolônico. E as 6 aminoquinolonas são substâncias que possuem esse grupo amino na posição 6 do núcleo quinolônico, e elas são amplamente utilizadas no nosso grupo de pesquisa como intermediários sintéticos, porque a partir delas a gente consegue obter núcleos como triazóis, tiazolidinonas e amidrazonas. Em relação às atividades biológicas dessas 6 aminoquinolonas, a gente pode destacar as atividades antivirais para hepatite C e HIV e também atividade antitumoral. Quando a gente fala em sensores de fluorescência, né, sensores fluorescentes, incluindo os sensores para detectar a variação do pH do meio, a gente tem 2 tipos de sensores. O primeiro deles é aquele ativável, onde o sensor, ele possui ali, o sensor, ele, ao interagir com o analito, ele passa a emitir um sinal luminoso, e então esses sensores já têm uma extensa linha de pesquisa hoje em dia, que são os sensores turn-on-off. E o segundo tipo é aquele com uma mudança ali na emissão modulável. Então, o sensor ele já apresenta uma emissão de fluorescência e, ao entrar em contato com o analito, ocorre uma mudança nesse comprimento de onda e ele passa a emitir com outro comprimento de onda. E esses sensores já são aplicados, já possuem diversas aplicações, podendo se destacar o monitoramento da qualidade de água, a segurança alimentar, diversos tipos de sensoriamentos em diversas tecnologias, e também na bioquímica, também na bioquímica como através de bioimagens, né, para detectar precocemente alguns tipos de doenças. E como motivação deste trabalho, a motivação surgiu quando, ao realizar um acompanhamento reacional de uma etapa de redução do grupamento nitro ao grupamento amino, nós, sob radiação de luz UV a 365 nanômetros, nós observamos que essas aminoquinolones, elas fluoresciam. Isso nos intrigou, né, nos fez pensar e tentar entender esse processo de luminescência das aminoquinolones. Com isso, o objetivo deste trabalho foi, então, explorar e caracterizar as propriedades fotofísicas das aminoquinolones sintéticas PB3, PB6 e PB10, modulando, então, a posição C3 do núcleo quinolônico, então, tendo-se o aminoéster, o aminoácido e a aminoamida, e comparando essas três substâncias com seu análogo estrutural sem o grupamento amino. Todas essas substâncias foram sintetizadas no laboratório de nucleosídeos, heterociclos e carboidratos na Universidade Federal Fluminense. Em relação à caracterização fotofísica, todos os testes, todos os ensaios de caracterização fotofísica foram realizados no laboratório de fotoquímica David Ernest Nicodem, na Universidade Federal do Rio de Janeiro, por mim, pela aluna Micaele Louise, pelo doutor Rodolfo Teixeira, sob supervisão da professora doutora Nancy Garden. Então, inicialmente, nós obtivemos todos os perfis de absorção no ultravioleta visível para esses sistemas, e como acetonitrila como solvente. Então, fazendo-se uma aproximação nos comprimentos de onda que compreende os máximos de absorção dessas substâncias, a gente pode observar que a presença do grupamento amino provoca um deslocamento batocrômico nessas substâncias, comparando-se com o seu análogo estrutural sem grupamento amino. Também é possível ressaltar, né, a presença de um ombro na banda de absorção máxima mais pronunciado ali no aminoéster e no aminoácido. A segunda etapa, então, foi obter, né, os perfis de emissão desses sistemas, e nós podemos observar o mesmo comportamento. A presença do grupamento amino provoca um deslocamento batocrômico nessas substâncias, e também é possível observar um deslocamento batocrômico referente a esses diferentes substituintes na posição C3 do núcleo quinolônico, sendo mais pronunciado para o aminoácido. A próxima etapa consistiu em tentar compreender como que essas substâncias se comportam na presença de ácido trifluoracético. Então, para o aminoéster, nós observamos que a adição de TFA acarreta numa supressão da banda de absorção máxima em função do crescimento de uma nova banda de absorção, indicando a presença, então, de uma nova espécie sendo gerada ali. E no espectro de emissão, a gente consegue observar a sensibilidade dessa substância frente à adição de TFA, onde concentrações bem baixas do ácido são capazes de provocar uma supressão na fluorescência da espécie neutra, e que possui um rendimento quântico de 9%, para um rendimento que passa para um rendimento quântico de 43% para a espécie protonada. Para o aminoácido, nós podemos observar que a diminuição de uma banda de absorção máxima em função do crescimento de uma nova banda de absorção ocorre sob concentrações altas, com adição de concentrações altas de TFA. E no espectro de emissão, a gente consegue observar um efeito oposto do que acontece no aminoéster. Essa supressão da fluorescência ocorre surgindo uma nova banda de emissão mais deslocada para o vermelho, no entanto, com menor rendimento quântico de fluorescência. Para a aminoamida, a gente consegue observar um comportamento bem similar ao do aminoácido. Ela também não é tão sensível à adição de TFA, são necessárias concentrações mais elevadas do ácido para que ocorra uma mudança. e para que ocorra, né, o surgimento dessa nova banda de absorção e emissão da nova espécie em função do desaparecimento da banda de absorção e emissão da espécie neutra. Então, inicialmente, nós pensamos, né, que essas novas bandas de absorção e emissão fossem referentes, na verdade, à protonação no grupamento amino. Então, nós optamos por realizar experimentalmente, obter, né, os espectros de absorção e emissão dessas substâncias, e nós podemos observar que, mesmo em concentrações muito elevadas de ácido trifluoracético, não ocorreu qualquer alteração nos perfis de absorção e de emissão dessa substância. Então, a princípio, isso fazia sentido com a nossa hipótese de que a protonação estivesse ocorrendo mesmo no grupo amino, mas, levando-se em consideração que na literatura já é estabelecido esse tautomerismo no núcleo quinolônico, a gente propôs um outro sítio de protonação. Então, há duas possibilidades para a formação dessa espécie protonada. A protonação pode ocorrer no grupo amino, gerando cátion NH, ou a protonação pode ocorrer na carbonila, gerando cátion OH. E para tentar elucidar qual dessas espécies ocorria, né, era favorecida, nós recorremos aos estudos de modelagem molecular que foram realizados em colaboração com os professores doutores Rodolfo Fiorot e José Valquimar e pela mestre Karine de Andrade, no laboratório LAMEC, na Universidade Federal Fluminense. Então, os cálculos, né, foram gerados pelo software Gaussian a nível de teoria DFT, com a função B3lip 6311++ de asterisco. E o que os cálculos inicialmente nos mostraram é que a espécie formada, né, favorecida, é a protonação na carbonila do núcleo quinolônico, que ia contradizir o que a gente estava imaginando, que o grupo amino era o sítio mais básico da molécula. Então, tanto o termo entálpico, quanto a energia livre de Gibbs, com valores negativos, indicando processos exotérmicos, indicam que essa substância, esse cátion OH, ele é favorecido. O mesmo ocorreu com a substância sem o substituinte amino, então a gente tem também um processo termodinamicamente favorável. E essa maior estabilidade do cátion OH, ela pode ser associada a dois fatores. A inserção desse próton nessas estruturas estabelece, né, uma ligação de hidrogênio intramolecular com a porção acila exocíclica. E isso pode contribuir entalpicamente para diminuir essa energia e também aumenta ali a hiperconjugação do heterociclo, aumentando seu caráter aromático. E para tentar elucidar, né, confirmar, na verdade, esse caráter aromático, foram calculados os valores de Nix. Então, o valor de Nix para a espécie neutra é de menos 1,70, para a protonação no grupamento amino é de menos 1,29, e para a protonação na carbonila, o valor de Nix é de menos 6,62, indicando, então, que realmente essa espécie possui um caráter aromático maior. E também foi possível calcular e plotar, né, o espectro teórico dessa espécie protonada, onde nós podemos observar que foi bem condizente com o espectro obtido experimentalmente. Enfim, a proposta desse aumento de rendimento quântico de fluorescência tão considerável no aminoéster, ela pode estar ligada, associada, né, a alterações nas geometrias envolvidas nesse processo. Então, para o ponto mínimo do estado excitado da substância neutra, há um ângulo ali no afastamento da planaridade de menos 30,63 graus. Já para a espécie protonada, esse ponto mínimo do estado excitado, ele tem um afastamento da coplanaridade ali de menos 0,5 graus. E com isso, né, a gente acredita que a inserção desse próton, a presença dessa ligação de hidrogênio intramolecular, ela impede a rotação dessa ligação C3 ', aumentando, então, a conjugação eletrônica. Isso vai favorecer a emissão radiativa por fluorescência, justificando, então, esse aumento no rendimento quântico de fluorescência tão considerável. Já para entender o mecanismo de protonação do aminoácido e da aminoamida, a gente precisa levar em consideração que essas substâncias já possuem uma ligação de hidrogênio intramolecular. Então, a gente continua tendo os dois sítios de protonação, o grupamento amino e a carbonila do núcleo quinolônico. E o que os estudos teóricos nos mostraram foi que ambos os processos de protonação são desfavoráveis, eles são endotérmicos e endergônicos. E, embora eles sejam desfavoráveis, a protonação na carbonila continua sendo o processo, o equilíbrio mais favorável. A gente consegue observar, né, a diferença na energia livre de Gibbs de menos 5,4 quilocalorias por mol para o aminoácido, e na aminoamida essa diferença é de menos 1,1 quilocalorias por mol. E essas pequenas diferenças entre os dois equilíbrios, a gente acredita que pode ser a explicação para essa redução, essa supressão da fluorescência dessas substâncias, porque agora a gente já não tem mais um equilíbrio apenas sendo favorecido, a gente já tem os dois equilíbrios de protonação ocorrendo simultaneamente. Uma outra observação que a gente fez, visualizando os orbitais moleculares de fronteira, a gente consegue observar que no orbital, que o orbital HOMO está concentrado, tem uma concentração ali, par de elétrons não ligantes do nitrogênio do grupo amino. E nós atribuímos esse ombro na banda de absorção máxima dessas substâncias como sendo referente à transição N-pi asterisco. Então, o próximo passo foi a gente tentar experimentalmente entender como que essas substâncias, o comportamento dessas substâncias, na verdade, frente à variação do pH. E nós podemos observar que para o aminoéster, do pH 3 ao 2, ocorre uma supressão da fluorescência, e para a aminoamida, essa supressão ocorre quase que completamente, variando-se do pH 3 ao pH 1. Para o aminoácido, a gente também consegue observar um pouco dessa supressão da fluorescência, no entanto, o mais interessante aqui foi observar o deslocamento dessas bandas de emissão para o vermelho. Isso é interessante no ponto de vista de biosensor, porque quanto mais deslocado para o vermelho, né, menor é a energia associada. Então, a gente garante que esses sensores eles sejam menos invasivos para os tecidos em sistemas em vivo. Então, a gente espera que a sensibilidade dessas substâncias frente à adição de ácido, elas possam ser aplicadas, né, para detectar precocemente doenças que estejam associadas a flutuações do pH, como, por exemplo, o câncer e a doença de Alzheimer. Como conclusão, a gente tem que os estudos de modelagem molecular elucidaram que a protonação do aminoéster ocorre preferencialmente na carbonila, do núcleo quinolônico. A protonação da substância PB2 e do aminoéster na carbonila são processos termodinamicamente favoráveis. A protonação, o aminoácido e a aminoamida, a protonação dessas substâncias são termodinamicamente desfavoráveis devido a essa ligação de hidrogênio intramolecular já pré-existente. E ao contrário do que aconteceu com o aminoéster, a adição de TFA no aminoácido e na aminoamida leva a uma supressão da fluorescência dessas substâncias, e a gente ainda está tentando entender melhor como que isso ocorre. E como perspectiva desse trabalho, a gente espera conseguir avaliar a sensibilidade do aminoéster e da aminoamida como um biosensor do tipo turn-on-off. E também a sensibilidade do aminoácido como um biosensor de emissão modulável. Gostaria de agradecer a todos os colaboradores desse projeto, aos organizadores também pelo convite e a todos os presentes pela atenção. Obrigada.
Thank you, Amanda, very much for your presentation. It was very, very clear and objective. We have time for questions. Okay, while people put some questions in the comments. Uma pergunta, Amanda. Você usou aí a parte de cálculo para identificar posições de protonação, né? Muito bem feito e tal. Agora, eu fico me perguntando, teríamos alguma evidência experimental que pudéssemos usar para mostrar a posição, se na amina, se naquele conjunto de carbonilas?
Então, a gente tentou, na verdade, né, experimentalmente, ver se essa protonação estava ocorrendo na amina, e a gente fez a caracterização fotofísica da quinolona sem o substituinte amino. Só que isso não foi tão explicativo, né? E por isso a gente recorreu aos cálculos. Mas a gente não pensou em como fazer isso experimentalmente.
Talvez o espectro de infravermelho não pudesse fazer identificação? Porque uma coisa é ligação OH, outra seria NH, ou não daria para diferenciar?
É porque infravermelho é muito difícil,
né?
Detectar. Às vezes essas substâncias elas formam dímeros e a gente não consegue observar esses estiramentos também das ligações OH.
Tá certo. Um outro ponto, talvez valha mais para os seus colaboradores teóricos, né? Que foi usado ali o cálculo do Nix para mostrar que havia um efeito de doação do par de elétrons do nitrogênio da quinolina, estabilizando lá o hidrogênio que ia, enfim, aumentando a aromaticidade do anel e automaticamente estabilizando o talpômero da forma enólica, né? Teria como comparar isso com uma quinona, onde esse efeito não poderia, essa aromatização não existiria? E aí você poderia ter uma ideia se isso realmente está contribuindo para estabilizar aquela forma lá?
Acredito que talvez fosse uma possibilidade. Não uma quinona, né? Mas uma naftoquinona, que aí seria...
Uma naftoquinona, não a quinona, mas uma naftoquinona.
Isso.
Equivalente sem o nitrogênio, né? Tivesse ali uma ligação C-dupla-O, né? Bom, let's see. Does you have any question? No question to Amanda? Okay, there is one here. Ok. Amanda, temos uma pergunta aqui, por favor. Júlio, quem está hoje com a gente? É Júlio? Pergunta, Amanda, é o seguinte. Congratulations on your presentation. Gostaria de saber se você fez... Bom, aí ela não sabe. To find the other possible de-excitation process. Porque quero saber se você fez um scan na posição do hidrogênio. Scan na posição do hidrogênio para identificar se existem outros processos de desexcitação. Eu não sei se o scan aqui, que foi que perguntou, Karine, esse scan, que scan é esse, Karine? Scan lá no experimento? What kind of scan you've seen? Você sabe responder, Amanda?
Não, na verdade, eu não saberia responder, não.
Queria saber, essa aqui é a pergunta, se você realizou um scan na posição do hidrogênio para saber se há outros processos de desexcitação.
Eu
não sabe como responder, né? Mais uma pergunta? One question that Amanda can answer, please. Valber Júnior, análise... What is NTO? Natural... What's NTO? NTO seria... Would be possible? NTO. Sabe o que é NTO?
Não.
Eu também não. Só está vindo pergunta difícil, Amanda.
É.
Fica mais fácil para você mostrar isso. Eu imagino que NTO tem alguma coisa a ver com natural orbital. Natural T orbital. Deve ser alguma coisa do gênero. Aí não foi você que fez. Okay, let's thank Amanda once more. Thank you very much for your contribution, Amanda. We move now to the second oral communication this afternoon. It is the communication of Matheus Signorelli. Let me see here, Matheus. Matheus is a PhD student in the laboratory, in the MolMod lab, under the supervision of Professor Luciano Tavares Costa. And Matheus will talk about molecular dynamics studies of the displacement and orientation of ionic liquids at the water vacuum interface. This is in the research line of ionic liquids, the molecular dynamics that Professor Luciano has been conducting in his lab. Matheus, thank you for your participation.
Hi,
presentation, please.
Okay, so thank you, Professor Volkmar. First of all, I'd like to say I'm very happy to be here, sharing some results and some discussion with you. And as said before, we will be talking about molecular dynamics study of displacement and orientation of ionic liquids at the water vacuum interface. So, first of all, let's start about the introduction of this discussion. It's the ionic liquids. So, ionic liquids are ionic systems with melting points below 100 degrees Celsius. So about the room temperature, we would have systems containing ion pairs that are like a melting salt. So they probably would have large radius to have the Coulombic interaction, a lower interaction about the charge, and lots of them could be made with organic compounds, and with make it possible to try to use it at the green chemistry and the science, the material science, and for medicine, energy, and so on. Well, for this work here today, we're gonna see two cations and two anions. The cations, first of all, is the C2-mine, the E-mine, that have an imidazolium ring and some alkyl chain, and the other one is the B-mine, called the C4-mine, that it's very similar to the other one, but have a large, bigger alkyl chain. And then the two anions, a chloride and the NTF2, that contains here in yellow we have the sulfur atoms, and on the red one we have the oxygens. The light blue, it's the fluorides, and as on the cations, the dark blue is about the nitrogen. So we have different kinds of ionic liquids, ionic pairs that can be made, 4 of them. And in one hand, we have the chloride, that's a very symmetrical anion with the charge of in all its sphere. And on the other hand, we have the NTF2, that it's a bit more structured and have different points of electronegativity and so on. So this is our main place to study, and we are now talk about very quickly about the molecular dynamics. The molecular dynamics can be used with classical or quantum mechanics, but at the beginning we studied with the classical mechanics, where the force can be found by from the potentials, okay? Take the derivatives from the potentials, and we can see them, the evolution in time. We have the frame by frame about the evolution of the systems in time, and then we can make lots of algorithms to make it better, to make it easier to apply it on different computers, and to analyze different sides about the problem in this situation. So here is a simplified schematics of the molecular dynamics algorithm. You can find here this on a lot of books and lots of pages on the internet, like Wikipedia. And for who not for who's that's not common, these schematics, these schemes could help to understand better what it's being done. So we have the initial atoms and with positions and velocities, and then we make we enter in a loop that see if the velocity changes, the positions are changed, and then we get the force that we can derive, as said before, from a potential, or if we use the quantum mechanics, from the wave function. And then we adjust all of this. We applied boundary conditions and control temperature, pressure, if we have a different ensemble, and we calculate then the output, and we make another step, and so on, in an interaction loop. Okay, so the details about this work that have been done, we used 25 ion pairs for each system. So 25 cations with 25 anions in a solution containing 2,000 water molecules. And for make this system, this initial system, we use the Pacmal software that we can found in the literature as described below. So we made initial cubic boxes. So about 4 or 5 nanometers, we made box, and we equilibrated by running an NPT ensemble simulation with 5 nanoseconds. Then, after the systems get to the equilibrium, reach the equilibrium state, we include, or each side on the z-axis, empty box, creating a slab of 4 to 12 nanometers cubic dimensions. Okay, so that was the main, the start of all this study. After that, for make the simulations, we use the GROMACS package. Okay, and for analyzing some of the results, we use the Travis software. And for the force fields, where you can use to predict the force and the energies, we use the Padua and Canonja force field for ionic liquids, and the TIP4P 2005 module for the water molecules, right? The temperature was set to be 285.15 Kelvin, and to control this, we use a thermostat based on the Viri scale algorithm and a coping time of 0.5 picoseconds. PME, the Verlet algorithm, and periodic boundaries conditions were also used. Okay, for long interactions, short interactions, and the boundary conditions. All right, so that's the simulation. Just to show you some of the results that we have here, we made a C2 min Cl 2nth nanosecond simulation here, as I can show for you. This slab simulation, as you may see, do not have lots of migration about the ions for the surface. But at the end of simulation, we can see that it started to be to be found some of the different regions where different layers of cation and anion. As we can see that the cation, in this case, the C2 min, are from the outside, whereas the chlorides are from the inside of the bulk. Right, to compare, let's see the similar slab, but with the other anion. Then we have the NTF2. And as you can see, from the pre-optimization, we already have a strong interaction between the ion pairs. Then, along the 20 nanosecond simulation, we can see clearly that the ions migrate for the surface, and they are sometimes of the displacement being in a pairs, right? So as you can see at the end of the simulation, all of the ion pairs, all of the ions, the 25 ion pairs, are at the surface for each side that are with the vacuum interface. So what we can get from these profiles, the last frame snapshot, just to show you the end of the simulation. Well, for systems like that have the chloride anion, we see that the distribution along the z-axis here is placed on the horizontal, right? So this direction is the z-axis, right? We can see that they do not make a complete layer on the surface. When we compare with the NTF2 anion, we can see clearly that have a lot of difference between them. The same results can be found on the systems with the other cation, the C4 min, and then we can see again the same profile, right? Okay, comparing all of them, we can see that it's very dependent on the kind of the anion and the interaction between the solvents with them, right? So here we have the surface picture about all the systems, and as we can see, that agree with last results. On the surface with the anion NTF2, we have a lot more enrichment phase, right? Okay, so let's see the mass density. Now that we already have seen the picture of the systems, we can analyze with more understanding of the quantity, right? So let's see. On the first line, we have the chloride anion, this 2-1, and in each column we have the different cations. So chloride in the first line. On the second line, we have the NTF2 anion, and each column have a different cation. Right. As we can see here, we can find it's the mass density from 15 to 20 nanoseconds, whereas the system had already get B on the final configuration. After 15 nanoseconds, the energy has been constant and then get the lower energy, and then we have a system that was equilibrated. So as we can see from these last 5 nanoseconds of simulation, we have the mass density of the cation from the C2-CL system. That's the cation are facing the outside of the slab, whereas the anion are on the inside. So as we can see, we have different places where the cation are, and from the outside we have the cation. On the inside of the bulk we also have, but in different places, right? And when we see the anion, they are from the inside as well. When you compare all of them, we can see something there. It's really interesting. If we have the NTF2, then we will see that the anion, it's a bit more, not a lot of more, but the anion now is from the outside. Now we have a different charge placement from the interface, right? And this can be found in all of these results of chlorides against the NTF2. Then we can see that with the different anion, we have different placements on the surface about the charge. To illustrate that, as we can see here, all of the different place where the ions are, but putting together all of the results, we have this picture, this large picture. So, okay, the charge density, right? As we said before, we have a different orientation for the charge, whereas the anion channels. So, to make this more clearly, we can see that when we place this charge density, we can see that the observations made before are the same. When we have a chloride system, that it's the first column, we have the negative charge for the inside, facing the bulk, whereas the cation, the positive charge are placing outside for the interface with the vacuum. And the systems get different when we have the NTF2 anion. When we have the NTF2 anion, the positive charges are for the inside, whereas the negative charge facing the outside, the slab. All right. The distribution. Here, it's a graph using the Travis software that it's calling that. From the last nanoseconds, as said as said before, we have all of these cations, and we can make a profile that estimates the quantity, the density, or the probability of finding different species around it. So we decide that we put just to analyze this hydrogen showed here on the x-axis, and some other atom like this carbon here on the origin. Then all of these C2-min, these cations, have the neighborhoods calculation about the species, and we can make a density profile about the probability to find different species around. Here we have the profiles of water around the cation, and as you can see, for the more we have the red color or the pink color, the more probability of have these species around them. So as you can see, we have the probability of finding water around the imidazolium ring, whereas the alkyl chain have no water around it, or very less raw. Okay, so as we can see, we found all of that. We can see that the alkyl chain is placed towards the vacuum, and with the last results that you saw, that we have a migration of the cation for the interface with vacuum, then we can see that the alkyl chain it's orientated towards the vacuum. All right, so here we have the anion around the cation, and as we see, we have the anion around the sides from the NTF2 systems and from below on the chloride systems, right? And here the final graph of this type, we can see that when we place the NTF2 anion on the same analyze software and same technique, we can see that water are placing above the below the oxygen atoms, right? And the fluoride atoms are facing towards the vacuum, whereas the cation are placing really close again to the anion, right? So and the mean square displacements. Here we have the displacement on the perpendicular plane from the z-axis. So where we see here the z displacement, MSD, we are saying that we have the displacement of the ions on a surface that is perpendicular to the z-axis. As we can see, the ions have a greater displacement on the plane xy that is perpendicular to z, which makes sense because especially when we talk about the NTF2 systems containing the NTF2 anion, all of them get to the surface, and we have the hypothesis that the ions can still migrating on the surface, and this maybe can have some applications, right? So the conclusions and observations, we have the greater migration to the surface systems containing NTF2 anion, the imidazolium ring solvation as already described in the literature, the difference in the surface polarity according to anions, as you can see, there's a difference if we have the chloride or the NTF2. We can understand the orientations of the neighborhood space around other ions and lateral displacements on surface. Okay, and what comes next? Study other ion pairs, see the temperature range, what can influence on these systems, study the multi-layers that can be made, the alkyl chain influence to where's the interface distance can it help to be, and the applications that it can appear. So I like to thank all of you, and in special the CAPS for financial, the STEAM of the Swedish financial, the UF, the Federal Fluminense University, the Uppsala University, that this work is in collaboration with an experimental group, and that I like to thank the professors of there, like Carl Keleman, Marie Madeline, and old Jhonathan. And my supervisor, Professor Luciano, and all of you, thank you. Feel free to send emails about the presentation or so on, and that's it. Thank you.
Okay, thank you, Matheus. Very good presentation.
Thank you.
We have
Welcome.
here some questions. Let's start with some questions from Professor Luciano, your supervisor. Professor Luciano is asking about... You could speak, you can read that, about applications of this methodology.
Okay. As we can see, it's a very what's the word that I'm trying to find? It's recent study. So I think that we can use it for charge transfer and some of the applications for energy, for battery storage, but it's this initial study. So as said before, we not always know what a person would be when they at the birthday of the person. So I really don't know the applications, but I'm really excited to find them. I think that energy transportation is one of the more probably.
Okay, thank you. There is another question from Brenda. Thank you, Brenda, for participating. Brenda asked you about the force field you used.
Nice. Thank you, Brenda, for the question too. Yes, this force field that was chosen, well, it's because of previous studies that the group already made and with accurate results. But yes, the OPLS was was thought about to be used, and in future studies, it's very possible. It's probably that we will test other force fields to compare and to see if the results that we already have are dependent on the force field. That it's very important to be related with the experimental results. So thank you for the question.
Okay. Continue with the questions. One question from Karine Andrade. It's about viscosity. I think it's come next to your screen.
About the Jhonathan, I think it's very interesting. Thank you, Jhonathan. Thank you for your question too. That's a very interesting topic that I not already think about it. The influence on the viscosities. I think it's probably yes, but I do not have the results. So to be honest with you, I prefer not to say that yes or no before I get into that. But really interesting. I can see it and send you an email after. I don't know, but really interesting. I probably yes because of the charge. It makes a lot of sense.
Okay, thank you. One question from Flávia, your colleague in the lab. It's about the correlation, ion-pair correlation, and the ionicity.
Really interesting. Flávia, thank you for your question too. There's lots of influence here, but the main influence that I found it's the interaction with the water. That, as we can see, when we have the chloride, that it's an ion containing a spherical dense of charge, that it's really solvated by water. But for the cations, the alkyl chain, it's the main thing to think about, because when we have this apolar chain, then it gets towards the vacuum, and that's why we want to study bigger alkyl chains to see the effects as the imidazole ring are solvated by water. Okay. So Raul said another one.
Just the moment when I have to speak, there is a construction here in the building.
It's
the problem. Yeah.
no, it's like here we have a lot of dogs, and always they are.
Okay, the last question from Raul. It's about the surface tension.
Okay.
And the comparison with experimental data.
Nice. Not yet, but it's one of the next steps that will be made, and to compare exactly with experimental data. All the results that we have, it's about are correlated with are related to the experimental data that we all have had with this collaboration with the Sweden research group. But in the next step, of course, we're gonna take other results. So thank you for your question.
Okay, Matheus, thank you again for your participation. It was a very interesting talking. We go now to the last oral communication. This is the communication from our invited speaker, Jhonathan Rosa de Souza. Jhonathan is a PhD student in the Universidade Federal do ABC, working under the supervision of our colleague, Paula Homem de Mello. The work of Jhonathan today, his communication is climbing the Jacob's ladder, the cobalt porphyrin case. Paula Homem de Mello likes to speak about the Jacob's ladder. This is also curious thing from the FT, density functional theory. Please, Jhonathan, the word is you.
Thank you, Professor Valkmar. Thank you, everyone that are watching you. And hello, everyone. As Professor said, my name is Jhonathan, and today I'm going to present to you some topics related to DFT and its functional. Let's climb some degrees of Jacob's ladder. So when we want to talk about DFT, it's reasonable to remind the fundamental equation of DFT. The equation shown here has some important considerations, and its terms has the following physical meaning. We have electronic energy for a given external potential. We have external potential and electronic density interaction. We have kinetic energy. We have also interelectronic Coulomb interaction. And as we know, we have the exchange correlation functional that is not is not defined in an exact form. And this exchange correlation density functional who works with DFT is just the reason of a lot of research spend some time designing new exchange correlation functionals. Several strategies was thought for designing this functional. And these different strategies to this functional and their results led to Jacob ladder's metaphor. So, for those who still do not know, Jacob's ladder is a Bible metaphor in which the ladder goes from earth to the heaven, connecting humans, more precisely Jacob, to God. In the DFT context, the base is represented by Hartree-Fock method, and the top is the chemical accuracy desired by quantum chemists. The steps between these two places represent the several approximations for exchange correlation of functional, going from more simplest to the more elaborate strategy to this functional. In this picture, it's possible to see some types of functional in which variables are considered in them. So we have from Hartree-Fock to heaven chemical accuracy. So when students start to study or work with DFT, they want to use more sophisticated functionals without climbing the lower degree that of the ladder. So they shouldn't just choose the better functional and the better approximation for this exchange correlation functional. But it's important to talk more about these functionals because some functionals are made to supply some strategies and to approach some systems and some specific systems. So let's talk a bit more about the pure functionals. That is the first degree in our Jacob ladders. The first steps, Jacob, this first step, it's composed by three types of functionals. We have LSDA, that depends on electronic density. We have GGA, that depends on electronic density and the spin density. And we have meta GGA, that depends also on kinetic energy of the orbitals. But an aspect that these functionals share is that they do not include Hartree-Fock exchange. And for this purpose, they are called pure because they are not contaminated with other methods. So they are DFT pure functionals. And the final equation that are made with this strategy is shown here. Where we have some contribution from the FT exchange and some contribution for the correlation calculated by the FT approach. And climbing up the Jacob ladder toward heaven, the next degree is composed by hybrid functionals, which could be also GGA and meta GGA as the peers, and depends on the same variable that the last ones. And the upgrade here is the inclusion of Hartree-Fock exchange with a percentage P, leading to the final equation as are being shown here. We have a contribution from Hartree-Fock exchange, and we have also a contribution calculated by DFT for exchange interactions. And we have the correlation calculated just from the FT approach. Getting a little more sophisticated and complicated, the last ones is the range separated ones. These functionals are also hybrids, but with an upgrade. They can also be GGA and meta GGA, and also include the Hartree-Fock exchange percentage. But the difference here is the Coulomb operator that is decomposed in two terms, in which the Hartree-Fock exchange action is constrained to a range of variable distance. This range is defined by the omega parameter, like here in this equation. The final equation for the exchange correlation is like that, where we have also a Hartree-Fock contribution. We have a DFT, a short range contribution for exchange interactions, shown in blue, and we have a long range contribution from Hartree-Fock exchange. And the correlation is for the FT approach also. So as you can see, there are several more steps to climb in which more sophisticated approximations will be made. But for our purpose here, we rose enough. In this context, it's reasonable to ask which degrees of approximation is accurate enough to simulate molecules. So until now, we climbed the degrees of the peers and the degrees of hybrid and range separated functionals. It's worth mentioning that there is several more degrees with more sophisticated approximations, but for our purpose here, we will climb just these degrees. So which degrees is accurate enough to simulate molecules? To answer this question and rationalize about developing new materials, in particular the molecular materials, a molecular model system, the cobalt porphyrin, was simulated by means of some different functionals, just to compare and see how these degrees, how these functionals perform when doing this kind of simulation. So this system is a start model system molecular for other materials that one desires to develop, because it's a aromatic ring and has interesting spectroscopy properties, and it's used in a lot of applications in scientific community. So dealing with DFT methods, the first point to be explored is the ground state multiplicity and energy, and all functionals applied here in this study yielded the doublet Ag as the ground state. The table show other possible ground state that was found as higher in energy that is the excited state than the doublet Ag. As you can see in the table, the doublet Ag, it's 0 in energy, and the other states, there is some value related to this reference. So you can see that the other states is higher in energy. In comparison to CI method showing also in the table, we see that the quartet B1G is the ground state, and the doublet Ag is not the ground state. So we can see that the functionals has some differences when dealing with ground states in molecules. Here is a graph representation of previous table, and it's possible to realize a non-uniform behavior between functionals applied related to excited states. As you can see here, the ground state is doublet Ag, and we have others possible ground states with an energy difference. And it's possible to see that the functionals perform in a very disform way when calculating these states. So once the ground states was defined, the molecular orbitals should also be explored in more details. So here we have the alpha molecular orbitals calculated for cobalt porphyrin. And here we can see that the alpha orbitals present significant differences. The pure functionals underestimate the HOMO-LUMO gap, as you can see here, and it's possible to see high proximity between Guterman orbitals and d orbitals, which is not expected. In hybrids, the Hartree-Fock exchange percentage change the order of some orbitals, and in the increase of the Hartree-Fock percentage also increase the gap, the HOMO-LUMO gap. And as you can see, also the range separation inclusion increase even more the HOMO-LUMO gap. And you can see also that there is some crossing between the orbitals when you simulate with different functionals. For example, if you follow the 24 Ag orbitals in blue is the d unpair orbitals. If you see the evolution along the functionals, you see that in the from BP86 from the omega B97X, you can see that the 24 Ag orbitals is lower in energy than the first functional that I said. So it's very complicated when you see a graph like that, because the functionals has different results for the same physical quantity. And here we have the beta orbitals, and as you can see here, also the 24 Ag orbitals is the unpaired orbital, and it's possible to see a different behavior when he grows up in energy and cross with Guterman orbitals unoccupied. So highlight also for this orbital and all the others d orbitals. As you can see in red, the d orbitals calculated by the peers present show energies higher than the Guterman's orbitals. That was not expected. So here we can see that the peers underestimate this gap and unstabilize the orbitals. Going further, the absorption spectrum is an interesting phenomenon to study and comprehend this functional. So here we have the absorption spectrum of a derivative of the cobalt porphyrin, the cobalt tetraphenyl porphyrin, that is the most common molecule used to be some experimental assays. And as you can see, we have two main maximum absorptions. We have key band in 2.3 electron volts, and we have B band 3.1 electron volts. So we have here the simulation of these excited states and the spectrum at all in a whole way. So the first important observation here is related to key band and the B band. The key band is composed by two pairs of excited state degenerated, and it's well described for all these functionals. Cavity for range separated, with the energy difference between these two pairs is higher than the other functionals, as we can see here in the diagram. Now the B band was not very well described in energy, because here the average value for all functionals was 2.5, and the expected is near to 3.1 electron volts. So it's interesting to see that for the pairs, extra charge transfer states was observed, just because that small gap in the orbitals diagrams. We can see that the orbitals provide these charge transfer states. For example, we have here in blue, in dark, the charge transfer states that do not appear in the global hybrid and in the range separated functionals. Okay, it's very clear that the state 1B, 1B1U, LMCT states suffer a huge variation of energy, because in PIR we see that this state is the first one, and when we go to the range separated strategy, we see that this states increase in energy and goes up after the B band, going to ultraviolet range in the spectrum. Okay, so as all these results show to us that climbing Jacob's ladder could be a complicated task, and it's prudent to benchmark the functionals for the desired application, because some functionals yield better results even it's not the higher degree in the Jacob's ladders. So these results was published in these articles that calls "Can one use electronic absorption spectrum of metalloporphyrins to benchmark electronic structures?" And here in this paper, we explore more other electronic structure methods, for example, NavPT2, to see how can I say, what can I say about electronic structure study based on absorption spectrum. I want to remind and be some acknowledgement for all the collaboration of these articles, Matheus, Yuri, and Paulo Mendimelo, that participate in this publication. And I want also to thank you, the organized committee of the workshop. I want to thank you, Federal University of Fluminense. I want to thank you, FAPESP, for the foment, for the scholarship and all the money for my research. I want to thank you and congrats the Federal University of ABC for the 15 years. Also thank you the graduate program in chemistry of Federal of ABC. And I want to thank you also the ABC Sim, our simulation group in Federal University of ABC. And thank you so much for watching. Professor Volkmar, I cannot hear you.
You don't hear because my phone was silent. Thank you for your contribution. It was very interesting, this talk about the behavior of the different functionals. There was a time when the computation of molecular property was very easy because we had no choice. There was no simple choice, no method to choice. There was only Hartree fork and post-Hartree fork. It was very easy. Today, life is difficult to those who try to do computational chem because there are a lot of alternative choice. Huh? Yes. But so it's life. Huh? Let's go to some questions. Let's see here. There is one from Professor Luciano. Could you generalize these obtained results for other similar compounds?
Thank you, Professor Luciano. Yes, we can generalize, but we have to be careful because sometimes the functionals behave in an unexpected way. But if you use these functionals, you can generalize mainly for aromatic compounds that we have a large pi orbitals extension, pi electron extensions.
There is a second question from Luciano. Have you systematically studied different metals?
Luciano, thank you again for the question. So we did not study other metals, but we made a search in the literature, and there is some works with iron and other metallic centers. But in our study, we just studied the cobalt case.
Do you know any study with iron porphyrin? Because iron is very, very, very relevant for living systems.
Yes. The iron porphyrin behaves in a similar way, but there is some tricky aspects about the charge transfer states, as we can see here. For cobalt case, we have difference, energy variation of charge transfer states. For iron, we have also this difference, and it's very complicated to rationalize or to say with accuracy what is the state and what energy is the more accurate for the molecule.
Okay. Now a question from Matheus Signorelli. Congratulations, very nice presentation. Is it interesting to use is artificial intelligence to make greater benchmarks?
Yes, Matheus, thank you for your question. Yes, it's very interesting, and there is a lot of researchers that applies machine learning and deep learning and artificial intelligence to rationalize, to make this benchmark. And sometimes you can see also neural networks applied to do some benchmarks for functionals and other methodologies that are similar.
Okay. In one of your slides, there was a lot of results with different functionals. It seemed that CompB3 is the most not converged
more
one.
Different.
It's true?
Yes,
more different. Because we have been using it for most of our problems.
Yes. I could not figure out what was causing this huge difference, but what can I say is that the result was that.
Strange, no?
Yes, I found it strange also.
Okay, and there was another one about the metal ligand charge transfer. There seems to be no convergence too. And this is one property that people are always very interested in. Oh?
Yes. We were surprised when we analyze the results and see these states. And as you can see, for the pure functionals, we have a lot of charge transfer states that the hybrids do not predict. But this is related, one of the aspects is the HOMO-LUMO gap that allowed some transitions between d orbitals and the pi orbitals. But yes, the DEFT, it's not very accurate for charge transfer states, mainly when we are talking about metal and organic systems, in this case, of course.
Okay, we have some time for additional question to Jhonathan. Karine, no question anymore? Okay. So, Jhonathan, once more, thank you very much to your contribution. It was very good, bringing us a lot of relevant information. Okay, we are now going to the last presentation of this session, the last presentation of our workshop. It is on honor, Professor Andrea Latge, to have you here with us. Professor Andrea is, I would say, one of the most relevant researchers in the Universidade Federal Fluminense. Among the physical community in Brazil, she has a relevant position. She, in addition of her scientific work, she has dedicated a large time of his work to the administration of the university. Along the last years, Professor Andrea has been in different positions, most of them connect to the Dean of Research and Postgraduate Studies. Today, she is the chair of this dean for, I would say, 3 years. And from the scientific part, she published 135 scientific papers with a high H index of 33 and citations above 3,000 citations. Professor Andrea, as I said, it is an honor to have you here. You was in our first and the last workshop, also to close our last workshop. But today we have you to talk about scientific, not about political subjects. And the theme today is driving electronic transport on graphene nanoribbons. This is a topic which a lot of people here in the Chemistry Institute have also been working. Thank you for your participation. Please, the word is with you.
Thank you very much, Valquimar, and thank you very much, Luciano, for the invitation. It was a very pleasure to be here with you. It's an honor to be here, actually, because it's very important to know the chemistry people, the work they are doing. We are very colleagues in material of the science we do together. I believe that I'm talking some kind of different things that have been presented here. I could not have the opportunity to be attending the workshop, but I give my all congratulations to the way they are conducted by both of you, by Valquimar and Luciano, and all the people that have been invited to be here. I learned about the invited people, very important person. They are talking about very up-to-date themes. It's very good for the students here in the Chemistry Institute. So my congratulations for the initiative that you have together with the chemistry community. I would like also to talk that I will try to do my best to pay attention to the people here. Are you talking about? I don't know if it's already. They are sharing my.
They share just now. Now it's coming. Okay. You just need to put in full screen.
Now it's okay?
Yes, it's okay.
Okay.
Nice.
I will not see the people, but I'm trying to believe that I'm looking at all of you.
Surely.
I try to give you a flavor about the works we have been done for some time. Not only me, but I, together with my students, other colleagues from my institute and abroad. And the main aspect that I will talk about today is about graphene system under strain. That can be talking about the straintronic and also about the valletronic, that are very important aspects from the graphene community today. I would like to say that I take part of INCT, an institute that is very important, that we have a lot of colleagues from Minas Gerais, that they are an important group from Brazil that have been working with materials made of carbon, not only carbon nanotubes, graphene, and other kind of two-dimension system. We also take part in a theoretical network financed by FAPERJ, that I believe some chemistry colleagues are also work with us in this network. And that we have been working mainly in this kind of non-structured material. And this is the name of a group that I take part in my institute. And I have been working for a long time with this kind of system that are nanoribbons made. They are some small parts that are taken from the graphene sheet, and we can do that by many kind of experimental aspect that can can cut this kind of system, that putting this 2D material only in a kind of almost one-dimension system that can have the very different aspect that depends upon of the edge they are cutting from armature and zigzag different edge. They present different electronic properties and transport properties we are going to show you in some details here. And we have been working together. This not only from the electronic properties, but we also have very paid a lot of attention concerning to the transport properties of these different systems. And we work not only with nanoribbons, we have put together some kind of hybrid system, putting together piece of carbon nanotubes together with some small nanoribbons, and we can detect some kind of different transport properties. And now we are investigating, we are putting some effort in analyzing topological properties of some kind of mathematical system that are present in the nature, also as named as Kagome lattice, that we can take profit of different flat bands that are very important from different aspects, and very recently are discovered some aspects concerning to superconducting properties provoked by these kind of flat bands. And so we have also been taking a lot of effort in describing some kind of, we call spintronic properties of this nanoribbon system. I'm not talking about too much about these themes here in this talk.
Professora Andrea, dá licença. Oi. A senhora pode apertar em ocultar essa barrinha? Ali no final, é a última, a barrinha lá no final, isso.
Here?
Isso.
No. I was not successful. I did something wrong.
Vai lá de novo e põe apresentar.
Yes. I lost my play? No.
Isso. Perfeito.
It's okay?
Okay.
It's okay? Okay, thank you. I'm sorry about that. But I was talking that we have been done some working concerning to spintronic, and here I show you some of the last work we have done that are concerned to corrugated system like this one, that have some kind of wave that are, and we can modulate this kind of system by only considering different parts of the nanoribbon. As I show you here, we have to consider, as I am interested in transport properties, I am concerned to have a kind of left lead, a right lead, and analyze how the electron can pass through a central part that we call conductor part, and we can modulate this central part as I want. And here I show you some kind of modulation that I can done, that it can be provoked by putting some different electric field of different direction, and can be simulated by introducing our Hamiltonian of the problem by include some spin orbital interaction named Hashba effect. And I show you here that by doing this corrugation, we lead some different concentration of charge, that it means that we are producing by this concentration of charge, different concentration of charge in the bottom part, in the top part of the orbital, like the PZ orbital here. We lead the induction of an electric field like that. And this can be introduced in our theoretical model by include a Hashba, a spin orbit interaction named Hashba interaction. And the thing that you analyze here that we call the spin-dependent conductance. That is, we try to calculate a physical response of the system when we, by an unpolarized current here, we obtain something that is polarized. Why it is polarized? Because we have different kind of response concerning to, we have spin up and spin down, that are different kind of spin in the electron spin, and we calculate a different quantity by the conductance of different spin and the same spin. So we can produce some kind of polarization, and by means of that, different central region have different response that we can calculate, and so we can analyze this kind of spin polarization. And not considering only a theoretical model like this one that I show you here, we can believe that an experimental situation can be produced, the same experimental situation can be reproduced by putting some different leads by gate voltage of different sign, producing this effect of a different sign of this Hashba effect that I showed you before. But I'm not talking about spintronic today, but I want to talk something concerning to valleytronic, and also a mix of valleytronic when you have some this kind of non-structured system where you have considered provoking some kind of strain in the system, and we can modulate this kind of mechanical deformation by introducing the concept of pseudomagnetic field, that is a kind of mapping magnetic field, but it's not a real magnetic field, but has this all the aspect of the magnetic field, so it is called a pseudomagnetic field. So the valleytronic that I'm going to talk you some aspects that we have been studying today is another degree of freedom of the electron, very particular of this bipartite lattice. That is the case of the graphene system, that we can say that we describe this honeycomb lattice as being populated by two different non-equivalent lattice, that name lattice A and lattice B. So it's called a bipartite lattice, and they have an electronic structure that is very, very famous. That these are the Dirac cones that has this linear response, this linear relation when we calculate the electronic structure, the electron level as a function of the momentum of the electron. And so it works like the spin up and the spin down, and here you have a K and K prime that differs the value of this bipartite system. So they rotulate energy extrema, maximum and minimum of momentum, that are degenerating in the momentum space. And so it introduces another potential like the spintronic concerning to the spin up and the spin down. It's another degree of freedom that has the potential to be used as an information carrier in electronics and optoelectronics. There are very famous articles and journals, a lot of paper that you can look at to know the application of this kind of physical response. So as I was talking to you, we have the honeycomb lattice, and so they are populated by two different triangular lattices that they are put here in different colors. And so the electrons in these two-dimensional crystals that have a honeycomb lattice structure possess this extra degree of freedom, in addition to charge, in addition to spin. So we can control this other degree of freedom and take profit of this to work with this kind of information, to code information in different ways. So these electrons populate these low energy states that are separated in moment space. They are in different position in the chi space. they have the same energy, but they have two wave number. They differs on the wave number, so we can control these quantum numbers related to the K and K prime valley. So the name is the valley electronic, has been because of these two different valleys that are these very, very famous electronic structure of the graphene system. And so there are a lot of literature concerned to that. These are some very smart applications of the valley electrons that goes to the reversible logical gate. I don't know very much about this theme, but there are very interesting literature concerned to that. They are taking profit of this duality of the degree of freedom of the valley of the graphene system to take profit as reversible logic gate and to work within the quantum computation system and proposal. There are other very interesting experimental work on the valley electronic. That's the group of Professor Jung-Sun, that they propose to take profit of a bilayer graphene system, and where they can control different by doing different gate voltage in the system. They can drive the electron current, but they are not concerned to the spin up and the spin down as you have the anomalous Hall effect, but they are concerned to different valley. The red and blue colors here are concerned to different valley, K and K prime. And so there are a lot of engineering that can be driven here to control the direction of these currents that are dependent on the valley of the graphene system. Here I pose also, I show you also another proposal concerning two different regions. That is a mixing. This is I like very much because it's a mixing of the effects of putting strain into the system. I show you here a system, graphene system that are submitted to external strain, and by doing so, we can separate the states that are rotulated by K and K prime and K prime valley dependent energy. And so by moving the region, the amount of region that are under the external strain, by changing the external strain, we can change the dimension of this system that are K and K prime, and promoting anomalous transverse current by only changing the wall that separates these two K and K prime region. It's a very, very interesting paper that we can read. I put here the reference to take a look. But for another point of view, the other thing that I was talking about to you, not only the valley electronic, but the strain electronic, is concerned to the possibility that by promoting some strain into the material, and this strain can be promoted by thermal cycles in the system, or by doing some growth of graphene on the, for instance, for a platinum surface, putting graphene on hexagonal boron nitride system, we produce, by the different mismatch of the materials, we produce some protuberation of the graphene lattice, and here I show you some kind of dome that are very, very clear to see here. And what is very interesting, as we can show you here, that the electronic is as it seems that you have by doing some calculation of transport, the differential by measuring with the STM measurement, you can dictate some very important states that are very similar to what happens when you have a magnetic field applied in this material. So these peaks are what we call pseudo-Landau levels that appear not because there is a magnetic field applied in the system, but appear because of the strain produced by the growth process in this system. So this, and what is very important to mention here is that the value of the pseudomagnetic field is a very strong value. That's not a real, of course, not a real magnetic field, but the effect is very important because it seems, it is like it has a magnetic field in this experiment, for instance, a 300 Tesla magnetic field value. And there are a lot of literature concerned to that. It was very important in the early of the 10 years here, that appear a lot of measurement in this kind of materials, putting graphene, growing graphene in different systems. And of course, it appears a lot of different experimental device that we can produce these nano wrinkles, these dumps, this pyramidal, and working with membranes, the graphene that are pending along a graphene layer that are pending when they are supporting by two leads. And there are a lot of experimental and even a theoretical proposal concerning to this kind of strain membranes and the strain graphene layers that can be described as it is producing some kind of pseudo-magnetic field. I like to show this experimental work that has been published in Nature. That is a group that is very clever on producing this kind of corrugation system, corrugation 2D system. And here I show you very clear the Landau levels that appear when they grow graphene on other substrates, but they produce a thermal cycle in this experiment that they can produce a pseudo-magnetic array very well determined, like this one. You show that there are a very consistent and very well-defined distance between the dips and through dips and peaks of the graphene layer in this system. And what is very interesting is that in this experiment, they by looking very carefully to these different regions, the peak and the deep region of the graphene system, we show that we can separate the two lattices, the two triangular lattices, the A sublattice and the B sublattice, and in a very well-defined way. Here I'll show this is when the STM point is exactly in the high position of this position here, the peaks of this graphene disposition here. And here is the blue region that is well beside the deep here. And they are only the yellow sublattice, only the green sublattice, so they have a very important separation of the two sublattices. And more important is that they, by very particular distance between this deep, they can produce, the flat bands can be produced like this one, that there are very small dispersion, energy dispersion in the A0, A2, and A3 that are the values of the energy are here. These are the experimental that they have and the theoretical description that they can do of this experimental work. And this is very important nowadays, that is the production of these flat bands, because they produce very correlated system that can even give rise to superconducting properties. And so there is a lot of material in the literature to analyze this kind of of a strained system like this one, and we can show that by moving the STM point, we can show that we find some different pseudomagnetic value along with the deep, along the strain of this system, and we can analyze, rotulate the pseudo-Landau levels and take profit of this system. So, motivated by all of these experimental contests, we have been done some theoretical model to describe nanoribbons that present this kind of mechanical deformation. We first of all we have been working with the Gaussian distribution, a very symmetric Gaussian distribution to these graphene nanoribbons, also graphene 2D material. And here I show you how the pseudomagnetic field are different, depend upon the mechanical deformation we put into your theoretical model, even in the experiment. So I show you that it's like a flower, that this is when I have the red color, I have positive pseudomagnetic field. When I have the blue color, I have negative pseudomagnetic field. And they are not unique value. They can change the values of the magnetic field, and so they are the way that the pseudomagnetic field appears depends extremely upon the geometry of the mechanical deformation. So we have done some work on these. We can calculate theoretically an expression for the pseudomagnetic field. This is done by doing a continuum model for that. But I have to say that the main aspect here is that we can include the mechanical deformation into the hopping energy in all the model that you have been working with that. So in this case, we put a centrosymmetric bump like this one. We get confined state inside the ribbons. We have found six-fold symmetry pattern in the local dense of state. This is the result. Here is the pseudomagnetic field, but here I show you the local dense of states of this material. And as I talked to you before, we also like the work of the work I showed you before. We got out the local sublattice symmetry break in each sector. So this is one of the work that we have been done that I like very much, is that we are able to promoting a separation of the valleys of the nanoribbon energy dispersion that I was talking about, the property that I am interested in, my group of all of us are interested in describe. That's the valley polarized currents. I show you here exactly the case that we can separate the transport in a kind of folded strain nanoribbon system. I can separate the currents that goes from one leader to another leader. That depends upon these are K valley currents. These are responsible for the K prime electrons in the system. So this is a work that have been published, I don't remember when, but this is a strain-fold assisted transporting graphene system. And so I show you here, when you have not a system with a mechanical deformation like this one, if I have only a nanoribbon with a zigzag edge, this is very important, the edge that we consider to analyze this kind of valletronic aspect. When I have this zigzag system and not including this deformed mechanical deformation, this is the electronic relation that you have. Energy levels as a function of the momentum of the electron. You see here K valley and K prime valley. And when you consider the fold, the deformation here, like this one I show you here in this design, we show you that there are some very perturbance of the energy relation, showed here in this region, showing this region, but no valley mixing at low energy are found. Here they are completely different. The K prime and the K valley, they are very separated from one from another. And the model that we use to describe the system, as I talked before, is a very simple model. We consider time-bound Hamiltonian. We describe the tensor, the strain tensor like this one here. This is a linear model approximation, linear strain model approximation. These are the way that we get for the pseudo-scalar gauge field, and we can calculate the pseudo-magnetic field by from this pseudo gauge scalar field. And here is how the hopping energy, this value here, the hopping energy of our model, change when you change the distance because of the strain you are considered in your nanoribbon. So you use the surface green function matching mode to calculate the conductance that depends upon the self-energy of the leads. And I use the Kubo-Landauer formalism to calculate the transmission amplitudes. That's the thing that you are interested to know about the transport of our system. And so, as I told you before, if you have an edge that is a zigzag edge here, I can promote for this. This is a numerical calculation from the nanoribbon to take a look at how intensity it can promote a pseudomagnetic field formation by doing this kind of mechanical deformation. And when you have a zigzag edge like this one, that it's not shown here, but it's a zigzag direction, we can promote a very high pseudomagnetic field. So we are changing the angle of the mechanical deformation, and these are the different regions of the pseudomagnetic field. Is not like the flower that I showed you before when you have the centrosymmetric Gaussian deformation, but when you have this kind of folds like this one I show you here, we have these strips that the blue are positive, negative, and the red are is a positive pseudomagnetic field. But when you have exactly the direction of the armature direction, you have no pseudomagnetic field. You have to have some particular direction of the perturbation concerning to the edges to promote the appearance of this kind of pseudomagnetic field. And by doing that, coming back to the electron dispersion, I can show you here that the probability density of finding the electron here are very dependent upon the K and K prime valley. So if you consider the two positive direction, that means the K2 and the K2 and K4 here, we can notice that one of them belonging to the K valley, they are very centrated, very located at the center of the nanoribbon. The nanoribbon direction is this one. This color means that you have a pseudomagnetic field very close to the center of your system, like the folded that I show you here. This is the edge. These are the edge of your system. So you have for this K2, you have all the states localized in the middle of your system, and the other one that is the same direction, the same electronic direction movement along the nanoribbon, we have they are spread more for at the end of your system. So the conclusion is that by doing this kind of folded system, this is kind of mechanical deformation, we can separate the current that comes from the K valley and from the K prime valley. So these are very important because we believe that by proposing this kind of folded system, we got a generation of quasi-ballistic transport channels. They are preserved. If you have the ballistic transport before the folded is introduced into the system, we are able to continue having this kind of quasi-ballistic transport, but they have produced, the fold has produced a broken symmetry, a broken sublattice symmetry, and the fold acts as valley polarizers, because we are able to separate spatially the state with different values. And one other thing that I didn't show you here, but these results are very robust against edge disorder. We have included some disorder, removing some sites of the edges of the edge, and the results are preserved against this edge disorder. But there are some drawbacks that is still present after this calculation that we can analyze. We need to analyze this. We need to separate the valley polarizer from the continuous extended state. And you believe we want to have a fingerprint to detect valley polarized states in experiment. So what next? What we did next? We include in our theoretical model another degree of freedom to try to take profit of this another degree of freedom, that is to include a real magnetic field. So this is the system without strain, without a magnetic field. These are again the electron dispersion I showed you before, with the K and K prime very well defined here. When you include a magnetic field, what happens is that appears that we provoke the system to show very flat bands that are very representative, very characteristic of magneticity, the Landau levels that we are introduced by putting this real magnetic field. And again, the way that we can introduce this magnetic field into our approach is in the hopping energy of our tight-binding Hamiltonian. So remember that our strain was described by also an exponential term in the hopping energy, but not complex. And here we can describe the presence of a magnetic field by this kind of, we call the Pios approximation, that is also changing the hopping energy of our system. So the zero field cones that are the zero magnetic field cones that are shown here, they are progressively transformed into flat Landau levels, like this one, very flat Landau levels. But you see that the zero state, this one, is preserved. There is nothing happened with the zero order state. Now this dispersive corresponds to the edge state. They are very feature of the nanoribbon graphene system, that is the appearance of the edge states like that. So here are the expressions of the Landau levels, the real Landau levels. And here I show you the electronic structure when we put together, the strain that is represented by this change of the hopping, and we put also together with the magnetic field. So the flat Landau levels that I showed you before, the flat, my God, I cannot show you. The flat Landau levels are changed to this kind of dispersive Landau levels. The deformation included, the way we do that here is the deformations included as a perturbation for the Landau levels. The zero, as I told you before, the zero level is not affected, the same one without with the perturbation, the mechanical perturbation, and the magnetic field perturbation. There is a broken degeneracy for specific K values. We produce some dispersive states at the ribbon center, and the gaps between Landau levels are reduced. So these are the panorama, the scenario that you have produced by the competition of a real magnetic field and a pseudomagnetic field formation that comes from the mechanical deformation. And the conclusions that we have here is that depend upon the intensities of this characteristic size. What is that? The B, I didn't talk to you, but the B, the small b value here, is exactly the size of the deformation have when you consider the deformation. The strain intensity is defined by an amplitude, that the way you put an out of plane deformation, and how the extension of the deformation that is defined by a size, a B size. So the rate of A and B is defined by a strain intensity that is we define like alpha here. And there is another characteristic size that is the magnetic field size, the radius, magnetic field radius. And we define a ratio between the magnetic confinement, defined by the LB, and the deformation width, that is the extension of the deformation. So depend upon this gamma value, if you have a gamma value much bigger than 1 and very small than 1, there are two regimes, different regimes, you notice that the states, the subelectric states are very different. Here we have a very well localized states. They are localized in the region where you have a very high intensity of the pseudomagnetic field. In this regime, the magnetic confinement allows the electron to follow the strain field profile, the strain field profile defined by the pseudomagnetic field. And at the other regime, the broadened Landau level states average the pseudo field over the deformed region, and you cannot have what happened in this other situation. So depend upon this, the value of the gamma. I show you some examples of different real magnetic fields, These are a set of 13 Tesla, and this is a set of 3 Tesla. And depend upon the rate of the magnetic confinement and the pseudo Landau level here, we have the opportunity to separate the K and K prime valley states or not. Here they are together. When we see in this situation, the K and K prime are not able to be differentiated in a measurement, not here, but here they are very well defined. We have this K and K prime resolution to say, this comes from the K valley. Cannot separate when the gamma is not small. So the important parameter here we discover in this kind of investigation is the ratio between the magnetic lens and the spatial even or not. The valley peak is a valley peak evolution in energy and position across the deformation. So this is exactly the size of the system. This is the edge of the system, the other edge of the system. When you have a condition that you can separate the valley states, is exactly like that, because the blue comes from one valley, K valley, and the red comes from the K prime valley, or vice versa, I don't know. And here in this situation, it's not possible to solve where the K comes from. They are mixed. So depend upon this very important parameter, we can solve to separate the states and to have a system that we get the valley polarization. So it's very clear to see that in this condition, it's okay, we get the valley polarization, and this condition we show here that is very impossible. It's completely impossible to detect from which valley the states come from. So we get the optimal conditions for creation and detection of valley split currents, are very well defined. We introduce extra conducting channels due to new states at the fold with energy within the Landau level gaps. The valley polarized channels appears whenever the sample is set up in the regime of the gamma plus lesser than 1 at chosen locations in the sample. And we get the separation of valley polarized states give rise to a unique braid pattern observable in STM measurements. So it's very important that in doing that, by doing this STM measurement, we can, depend upon where we are, we can get this separation of states. And so the engineered deformation can allow us for collecting individual valley current. But you want more. You want to be able to switch the currents from the leads. So if you have different currents coming from K and K prime valley, we can, we would like to be able to detect this kind of selected current, valley-dependent current. So you propose to put other leads, not only the right and left and right leads, but complete the system by putting another lead into the system. Now we are working not only this top and bottom lead, but with the quantum Hall regime, putting more than 6 leads to analyze some different conditions to the system. So we switching valley filter kitchen directions in multi-terminal graphene system. That is the area that you are working on nowadays. So the ingredient, the tools that we took all together are the fold-like deformation, the mechanical deformation. This is the mechanical, these black lines here give us the fold that we have considered in this theoretical model. We consider an external magnetic field and consider different leads, top, bottom, left, and right. And the challenge of this investigation is to exactly have the appropriate conditions to get valley filter transport and to switch filter current direction. So it is very important to show you here that when you have no magnetic field, but when you have only the mechanical deformation, the mechanical deformation is measured by this percentile here, 5, 10, and 15%. It depends upon the intensity that we put the A and B parameters that I described before. We can show here that the K and K prime transport, that you do some calculation that is K-dependent calculation, have this condition very well defined here. We show here that the left-right current coming from the K valley there is no contribution, while the K prime valley has an intensive contribution. So that is the first results that you have from the first investigation. From this, with no magnetic field, we already have a valley polarized transmission in a broader energy range, depending, of course, on the intensity of the perturbation, the mechanical deformation. So the folded deformation is able, only this default deformation is able to promote a K prime filter in the top lead. So here I show you the states, the probability density that we have from the state, the state coming from the first band, the second band 2, the 3, the third band, the fourth, and the 5, and I show that they comes from the K prime, the K valley, and the K prime valley, or vice versa. It doesn't matter, but it's very different. They are spread in different regions of our sample. So by considering only the filtering in this kind of promoted design that you put 4 leads, right and left and top and bottom, we can show you here that we promote the K prime filter in the top lead. So by analyzing the electronic structure and the distribution, the electronic density along the system, we notice that we have promoted a K prime selection of the transport. But if we include also the magnetic field, an interesting separation we can show here for when you have the two contacts and when you have the four contact system. Here are the results for the left, right, the transport left, right, left and right. When you have four contacts in the system or two contacts in the system, clearly the green and orange results are the K and K prime contribution. When you have only two contacts, we have no filter of the K and K prime value. But when you have the four contacts, as we push the states up to the edge of the system, we can do a selection of the states from one of these, the top, because as you have the magnetic field only, there is the results for top and bottom lead are different, but we can promote a filter along the right and left transmission, depend upon the energy, of course. There is not for all the energy, but there are some range of energy that we promote a filter in the K and K prime value in the transmission, right, left, and right. These are showing more detail here, but I have to show you that it's not only the same parameters that we used before when we have the theoretical analysis, that we didn't put 4 leads, but we are considered only 2 leads. We show you that the main parameters that are important is the relation between the magnetic field and the station of the deformation. Here we have to introduce another parameter to be able to detect if there will be a K and K prime filter in the system, that is the strain spread in the system. So we have the strain intensity that as before is given by this rate. We have the relation between magnetic confinement and deformation width that we used before, but we have to consider another ingredient, that is the extension of the deformation spread along the system compared to the size of the nanoribbon. So we did some discussion between these parameters that are not so easy to describe every one of them. But here I show you that depend upon the strain, these different colors are concerning to different strain intensities, and these are the parameters that I said you before, that is the relation between the magnetic intensity and the deformation of the system. But we can find the interval of the energy that we can be able to notice a valley filter transport. So I finalize here as a general remarks, saying you that the graphene system with extended mechanical fold-like deformation and under applied magnetic field, we did an enhancement of valley filter transmission. The valley filter currents are obtaining a broad range of energy, and it can analyze this broad range of energy, analyzing the different values of these parameters considered here. We are able to control the direction of the valley filter currents by introducing these top and bottom leads. And we did a threshold maps of confinement parameter, magnetic involving magnetic, strain extension, and ribbon width to optimize the filtering and switching process. And so multi-terminal graphene system can be proposed as possible setups for filtering and switching valley polarized current directions. So if I finalize my presentation here, presenting the people involved in all this work. These are a woman group. These are a colleague from Ohio University. This is a student, PhD student that now is working at Latge in Nova Friburgo. Vanessa has done his PhD here in Federal Fluminense, and now is a postdoc work with me. And there are not only women, but 2 boys also involved. That is another PhD student that now is working in Spain, in Bilbao. And this is a collaboration that comes from the group of Ohio University, but he's a professor at Mexico Institute. Thank you for attention. Very happy to be presenting all this work here.
Okay, Andrea, thank you very much. A lot of information.
I'm sorry. I'm sorry about that.
This shows it is very profound.
It's a history.
Yes. Okay, we have here some questions, two from Professor Luciano, and the first one is about the challenge regarding the theory and the computation. For us in chemistry, these are 2 points that are always critical. We frequently have difficulties with our theory and with our capacity to do calculations. What about your work in the field?
I know that because nowadays, all this work, Luciano, has been done with working with tight bind model. That's a most simple model compared to the FT calculation that you are used to work with, and other tight bind from first principle that I know that are very hard calculations that depends that involves a lot of time. I'm in a group that we are trying to do a comparison between tight binding calculations and DFT calculations, and in many aspects. And it's very interesting because sometimes I say, come on, so many time involved in this calculation. But and sometimes when I include, because it may not in these works present here, but I'm very involved in some calculations that we put electronic correlation also in our model. And so it takes a lot of time also, because you have to do self-consistent calculation, charge, and charge depend upon the charge of the system. But the chance that we have here is that by using this kind of simple model in graphene, and by work with graphene, it's able to do that because of the number of orbitals involved in this system. There are very few electron systems, so it's possible to do, because the DFT calculation next to the Fermi level are very similar to our tight bind model. So we are we are free to do that. But it's interesting because we can include many aspects that are very different to include in the DFT calculation. The strain, the electric field, the magnetic field, and a lot of perturbation that we can do. That's not so easy when we go to more in this area of DFT calculation. But I have to say that by working with this system, very simple system like carbon material, we are safe in doing that. But it's important, of course, it's important to always to be comparing all we do with the other kind of calculation.
Okay, and the second question from Luciano is about the operational skills. How do you introduce the deformations in your system?
The deformation is included exactly in the hopping, because we know that when you put the deformation, we did a perturbation in the distance of the materials. So in one of my slides, I show you that there is a difference between the lattice parameter, and when you put the strain, this can be an in-plane deformation, can be an out-of-plane deformation, and so we change the distance between the atoms, and so we introduce this kind of linear theory elastic perturbation, and so it is the hopping energy change. And by changing this hopping energy, so there is a kind of calculation that we can map the appearance of a pseudomagnetic field. This is like that.
Okay. There are some other questions here. One that I cannot understand the meaning is from Valber Jr. Nice presentation. Did you calculate the figure of merit ZT?
Now, the figure of merit ZT is when I do the thermal electric properties. I can do that. I have been working with that, but nothing concerning to what I have presented today. But I by doing this kind of transmission relation that I put in a slide, in one of the slides, I can also calculate the thermal conductance, I can calculate the seebeck effect, and by doing that, I can calculate the figure of merit. But I have to calculate, to be honest, I have to calculate also the phonon, that is the lattice thermal conductance. And this is another capture that I have to introduce in my theoretical model that I have never done. But I can only calculate the ZT, the electronic ZT component.
Okay. There are two questions, one from Professor Lilian Weitzel and another one from Professor Rodolfo Fiorot, that I will put both together. It is about the defects that you can introduce in the graphene. For example, if you can open and free space, or you can put some heteroatom, for example, what is the excess of electron, or is less electron than carbon, for example, boron, nitrogen. What happens?
Yeah, of course. Actually, I have done some work with that guy that is now in Bilbao, in Spain, the Carlos Leon. We have done some nanoribbon calculation that in the middle of the graphene nanoribbon, there is a strip of boron nitride. And so we did this calculation. In that work, we have done a very different tight bind model because we have to introduce some other potential because there are two different systems. One that is extremely high semiconductor system with a large gap. And in that kind, we are interested in putting some boron or nitride in different regions of the graphene region to analyze the diffusion of the possibility of diffusion of this defect into the other material. But it's possible to do that. I can show you if you want a literature about that. It's very important. Mm-hmm. And also the vacuums is also possible. You can do some vacuums, removing atoms, and so there will be normally it appears a magnetic moment at the edge of these vacuums, and we can analyze how it happens, the transport, and many things we can do that.
Have you studied the consequence of these defects to absorption, gas absorption, for example?
Not exactly, but you are with Pedro Venezuela. Now you are working not on graphene, but you are working graphene that is some carbon materials also, but there are different configurations from the graphene system. And we have done some calculation putting some metal absorbing the material like titanium, iron and manganese, something like that. And now we are trying to put in gas to calculate the probability of adsorption because of the functionalization on the graphene system. We are working on that exactly in the moment.
Okay. One comment more from Luciano. Luciano is inspired. About the Nobel Prize 2010. Please comment about the advance that theoretical calculation have promoted during the last 2 decades.
Come on. There's a lot of contribution. We showed that after the Nobel Prize, a lot of work has been done in graphene. And when you think, they have done everything. No, they have not done everything because even as I comment in my presentation, I believe that 3 years ago, they discovered the possibility of having superconductive in these materials by putting bilayer system and producing this kind of moire pattern that are very important. Exactly by producing these flat bands, this very correlated system, they can produce superconducting properties of these materials. So I believe that, and they are working on topological properties of these materials. I believe that many works can be done with graphene. And this is an area that also this kind of electronic possibility on computation devices and many things. I believe that we are you expect many other improvement in these areas, is my opinion.
Okay. One comment. This Andrea Geim is the one who won two Nobel, not just two Nobel Prize, but two prizes, no? One
Two
about
prizes. One Nobel
yes.
and one Nobel.
A Nobel, yes.
The frog.
The first one was the one, yeah, yes. Why was he studying the frog? Yeah. Okay. And another one, more technical, from Ankit Karageti. Do you use the same Hamiltonian for electric field in DFT in tight binding approximation?
I don't know if I know exactly how to use the electric field in DFT calculation, but I can do in many aspects, because when we can depend upon the direction of the electric field, we can include it is only by a different gate voltage in our system. When you put the bilayer system, it's like we can put all the atoms here in an energy level and all the atoms here in another energy level. But when we put in the in-plane, we have to do some kind of calculation. We can do some Poisson formalism that we can have to do a self-consistent calculation, calculate the charge of each of one of the charge lines we have, or we can only do a kind of linear dispersion that is promoted by changing the electric field from one side to the other side of the system. It depends upon. I don't know exactly how it's included in the DFT calculation, so I cannot answer very well your question. Sorry.
Okay, I think we are just in time. Andrea, once again, thank you very much for your participation here. It was very illustrative to us.
I am really very proud.
We hope to have you in the future workshops.
Okay, I will be very, very happy again if you invite me in the third workshop. And I want to have new things to talk about. And it's wonderful to have the opportunity to talk about my scientific work. That is what I really love to do.
Okay,
and
okay.
It's very important to the student that, because I want to, I don't know if I would like to tell you, all of you, that I am here in Acre today because I am taking part in an event that is a annual meeting of the Pro-Reitores, the Dean of Research and Graduation course in Brazil. And you have the opportunity to have different persons talking about the difficulties that we are going on Brazil. And we have to be very honest, because we have the Dean of CNPq is here, is just here in the moment. We have the opportunity to hear Luis Davidovich, that's one of the very important person in science nowadays, in my opinion. And he's very not only smart in the physics he has been done during all his life, but it's very important to have this person defending the science. And I would like to say you don't give up. Don't give up that you are going to pass this to another level.
But did you read the Jornal da Ciência from today?
No.
ABC?
No.
CAPES caminha para o desmonte do sistema de avaliação da pós-graduação no Brasil. Indeed, they did it. CAPES já desmontou o sistema de avaliação.
You know that my friends from physics?
I know, yes. They give up their position in the commission, the evaluation commission. And a lot of other commissions are doing the same one.
I hope so.
Indeed, the evaluation from the post-graduation in Brazil was in the past. At least for this year. Em português. Não sei se você viu também que a presidente da CAPES divulgou hoje dizendo que os dados da sucupira serão preenchidos apenas na próxima década.
She gave us a seminar here. She gave us. The Dean of CNPq has come here. Yeah. But she was not here. She was only in video, and she didn't give the chance of answers and of questions, not questions. Yeah. And after that, she went away, and she put this notice in the mail.
Yeah. I think we are in the worst moment for the post-graduation student in Brazil. From the last 3-4 decades.
I agree with
very difficult moment.
Unhappily, I agree with you. But
yeah.
let's go.
Let's resist.
Yes.
Yeah?
Yes, that is.
Okay, thank you. We are going now to close our workshop.
Thank you very much.
And okay, I asked Luciano to say the last word because he was the organizer of the workshop. He's with her very, very, very important group. So he said to me that he has things to do with her kids. So I have to say the last word. E vou dizer isso em português, porque meu inglês não é suficiente para falar, enfim, fazer um leve balanço aqui do nosso workshop. Thank you for all the people from abroad that participate in our workshop. It was and is very important to know that a lot of people from other countries could participate in the workshop. We are very happy with this. Thank you very much for your participation. Ok, agora para os colegas aqui, enfim, do grupo, não sei ainda quantos estão por aí, espero que esteja ainda um número razoável. Nós estamos fechando o nosso segundo workshop. O primeiro aconteceu em novembro de 2019. Em princípio, o planejamento é para que tenhamos esse workshop a cada 2 anos. Não falei com ninguém ainda, mas vou tentar convencê-los a todos de não fazer o próximo em novembro de 2023. Porque, obviamente, todos nós, enfim, exatamente o grupo que participou da organização desse aqui, estará envolvido na organização do SBQT, e organizar 2 simpósios ao mesmo tempo vai ser extremamente complicado. Tá? Agora, por outro lado, enfim, eu não participei da organização, enfim, o grupo aí sabe, exatamente porque eu estava na organização do SBQT, eu não tive tempo para ajudar vocês. Né? O Luciano adicionou meu nome ali no comitê científico, mas só por uma questão de honraria ou coisa do gênero. Mas foi muito bom. Eu não sei se o resto da audiência concorda, mas eu achei excelente, excelente. Né? Tivemos conferências muito boas e tivemos a participação dos nossos alunos de uma forma que me surpreendeu muito, porque foi muito expressiva, né? Foi muito expressiva. Então, eu fiquei extremamente satisfeito com o conjunto, com a organização como um todo, com o resultado do workshop. Luciano, enfim, pelo menos eu não tenho mais como fazer isso, mas ele ainda tem, arrancou alguns cabelos com a preocupação da maneira, enfim, do instrumento que nós iríamos utilizar para realizar o workshop, né? Mas, ao final, ele terminou encontrando esse grupo do Instituto Sua Ciência, até anotei aqui, Instituto Sua Ciência, a quem eu agradeço, e certamente o Luciano agradece também a disponibilidade de nos ajudar. Obviamente que foi um serviço pelo qual nós pagamos, né? Mas quando a gente paga por alguns serviços aqui no Brasil, a gente nem sempre tem o retorno que nós gostaríamos de ter. Isso, inclusive, aconteceu no workshop de 2019. Pagamos alguns serviços, não tivemos o retorno desejado. E com esse grupo aqui, pelo menos as pessoas que nos assistiram nesses 4 dias tiveram, na minha avaliação, de novo, um trabalho que foi muito bom, sempre disponíveis, né? Pessoas muito agradáveis para trabalhar e provavelmente serão procurados em eventos futuros, né? Então, o pessoal aí do Instituto Sua Ciência, a coordenadora é a professora, que eu agora esqueci o nome, lá de Itajubá, eu acho que é a coordenadora, mas também para o pessoal que esteve aqui com a gente, muito obrigado pela participação, pela ajuda aqui para a gente. E, enfim, eu, pelo menos, acho que eu não tenho nada a reclamar. Tá? Agradecer, obviamente, ao grupo que atuou ali diretamente na organização. E se eu conseguisse aqui, se eu não fosse tão desorganizado, e por isso que eu não participei da organização, eu conseguiria saber quem foi. Deixa eu ver aqui. Mas, enfim, vou começar aqui pelo de baixo para cima. Tá? Então, os alunos, muito obrigado aí pela disponibilidade de ajudarem a gente. Está aqui o nome do Matheus Ruas Miranda Signorelli, o Henrique de Castro Silva Júnior, a Karine Nascimento de Andrade, a Flávia Cristina Assis Silva e a Milena Diniz Lessa. Tá? Então, muito obrigado pelo trabalho de vocês. Eu tenho certeza que o grosso foram vocês que fizeram, né? A parte mais operacional da coisa ficou com responsabilidade de vocês. Sem destacar o trabalho de ninguém, mas lembrar que o Henrique vai defender sua tese de doutorado amanhã, e, portanto, certamente ele tinha muito com o que se preocupar nos últimos tempos, e a Milena tem a sua defesa programada para o começo de dezembro, daqui a 15 dias, mais exatamente. Eu acho que sim. Ou daqui a 8 dias. Enfim, ou daqui a 8, enfim, em uma ou em 2 semanas. Né? Não, mas é em 2 semanas, daqui em 15 dias. Então, também uma pessoa que está, obviamente, enfim, tem muito que se preocupar, né? Não só nesses próximos 15 dias, mas também nos 15 dias que passaram nos tempos passados. Então, mais uma vez, muito obrigado a vocês pela disponibilidade em ajudar. Tá? E também os colegas professores que, enfim, se dispuseram a colaborar. De novo, estou aqui vendo o nome do Rodolfo Goetz Fiorot e o Fernando Martins dos Santos Júnior. Então, pelo menos, se não houve um equívoco de quem organizou aqui o evento e colocou o Organizing Committee, foram essas as pessoas que participaram na organização. Não é um processo simples, a questão da escolha dos nomes, o nome que na última hora disse que não pode vir, esse fato que o Luciano ficou até o último momento preocupado como é que iríamos conseguir organizar isso. Agradecer à PROP, porque nós, em algum momento, recorremos à PROP para usar a conta institucional da PROP. A PROP tinha se disponibilizado a nos fornecer a sua conta institucional para que fizéssemos o evento pelo Google Meeting, que era a única, enfim, apenas a conta da PROP tem capacidade suficiente para atender o grupo de pessoas que deveria participar do evento. Portanto, obrigado à PROP, mesmo nós não tendo utilizado, mas foi muito importante. Agradecer, que eu não sei se está aqui na minha frente, e não vejo o Luciano, mas... Então, está aqui, né? Foi oferecido um curso, mini curso, onde vários alunos participaram, desde terça-feira, terça, quarta e quinta, e para o oferecimento deste mini curso, as instalações do Laboratório Nacional de Computação Científica também foram fundamentais. O LNCC, claro que o Luciano teve que apresentar um projeto normal, mas o Luciano apresentou lá a proposta, enfim, informou qual era o objetivo da solicitação que ele estava fazendo, e então logo ele fez a solicitação, ele foi atendido e o curso foi oferecido. Espero que tenha sido proveitoso para todos os alunos que participaram. Tá? Já agradeci aqui a PROP, enfim, que em princípio estava disposta a nos ajudar com a questão da transmissão. Os laboratórios principais que se envolveram, enfim, têm se envolvido com isso, que é o laboratório coordenado pelo professor Luciano, o MolMod, o laboratório coordenado pela professora Célia Ronconi Lamec, que está aqui, o laboratório de Química Computacional, que eu coordeno. Tá? Obviamente que agradecer ao Instituto de Química da UF, muito embora nós não tenhamos utilizado as instalações diretas do Instituto de Química, certamente, se precisássemos utilizar, eles estariam disponíveis. Agradecer à UF, antes da UF, o programa de pós-graduação. A gente também, sempre que precisou do apoio, da coordenação do programa, sempre esteve à disposição para nos ajudar. Agradecer à universidade como um todo, enfim, a gente às vezes espera, e tem que esperar mesmo muito mais, ela não consegue nos oferecer tudo aquilo que nós gostaríamos que fosse oferecido, mas na medida do possível a gente consegue realizar as nossas coisas aqui na universidade, e mesmo, pelo menos na minha opinião, que a universidade somos nós. Não adianta nós querermos nos referir à universidade como sendo uma terceira pessoa, porque não é. Eu sou a universidade, eu faço a universidade, e assim é com cada um de nós, professores, alunos e servidores que têm vínculo formal com a Universidade Federal Fluminense. Então, é a universidade que eu quero fazer crescer, é a universidade que eu quero ver evoluindo. Então, agradecer à universidade. E, por fim, esse órgão que eu, particularmente, tenho falado muito mal nos últimos tempos, que chama-se CAPES. Né? Mas, de qualquer forma, né, é o órgão que nos apoia. Né? É o órgão que nós estamos, todos nós, vinculados a um programa de pós-graduação. As pós-graduações no Brasil são coordenadas, são gerenciadas, são organizadas pela CAPES. Tá? O nosso evento, o workshop, ele está dentro da programação do projeto de internacionalização da UF, o chamado PRINT CAPES UF. É um projeto que é financiado pela CAPES. Possivelmente, algumas pessoas aqui já me ouviram me referir a esse projeto como um projeto de desinternacionalização. Não pelo projeto em si, mas pela enorme dificuldade de usar o auxílio do projeto, enfim, pela burocracia, pela maneira como é feito, e principalmente a minha crítica pessoal é porque havia, antes do print, havia um programa que, na minha opinião, facilitava muito mais esse processo de internacionalização. A mobilidade de estudantes, por exemplo, vários dos nossos estudantes estiveram no exterior sem nenhuma dificuldade, né? A gente, bem ou mal, conseguia trazer alguns pesquisadores de fora, e isso não só diminuiu muito, agora, por exemplo, chegou a zero, mas as bolsas aqui também chegaram a zero, né? E, enfim, nós estamos, como eu acabei de falar com a professora Andrea, as notícias que têm chegado nos últimos tempos, tempo significa dias, eu não sei se vocês estão acompanhando, mas são notícias extremamente preocupantes. Vocês não imaginam o que é a CAPES chegar... Ela não, se perguntar para ela na pessoa da presidente da CAPES, ela vai dizer que não. Mas o comportamento dela é exatamente isso que a professora Andrea falou. Ela vai nos locais, fala, não dá oportunidade para ser questionada e pede que qualquer coisa que você queira criticar, comunicar, que mande um e-mail. E-mail que não é respondido nunca. Tá? Mas o certo é que a CAPES, ela simplesmente acabou com o processo de avaliação das pós-graduações. Tá? Isso aparentemente ficou no passado. Uma coisa inimaginável há 2 meses. A Comissão da Química trabalhou arduamente a partir do mês de julho, entre os meses de julho, agosto e setembro, trabalhou duramente no processo de avaliação, estava com quase tudo pronto, para chegar no final de setembro e dizer, olha, parou, acabou, não tenho mais interesse nisso, isso não interessa mais para a CAPES. Tá? Enfim, é uma crítica que a gente faz, dura, mas que eu acho que, enfim, principalmente os nossos alunos têm que ficar cientes que nós estamos em uma fase extremamente difícil. Tá? Extremamente difícil. Como, do ponto de vista da pós-graduação, eu não lembro de ter passado por um processo tão complicado como esse que nós passamos agora. Tá? Mas a realidade, mas de qualquer forma, nós pagamos, o recurso que nós pagamos ao Instituto de Sua Ciência, pagamos com o dinheiro do print. Então, muito obrigado de qualquer forma. Havia e há o print, né, para apoiar a realização dos 2 eventos. De qualquer forma, o que resta é isso que a professora Andrea falou agora há pouco, é resistir. Tá? Temos que ser o mais resistente possível. E esse tipo de atividade que a gente faz aqui é um tipo de resistência. É dizer, olha, nós continuamos vivos, nós estamos trabalhando, nós estamos fazendo, não vamos arredar o pé, estamos aqui. E é isso, né? Tanto do ponto de vista nosso, docentes, quanto do ponto de vista dos alunos. Obviamente que do ponto de vista dos alunos é muito mais difícil. É muito mais difícil. Né? Mas, enfim, temos que ser persistentes. Não podemos jogar a toalha. Temos a esperança, e a esperança, como todos sabem, é a última que morre, temos a esperança que um dia isso passa. Espero que seja rápido. Tá? Vamos torcer para que não demore mais tanto tempo esse período tão duro pelo qual nós estamos passando. Tão duro pelo qual nós estamos passando. Né? Bom, é isso. Não sei se temos mais alguma coisa. Não sei se temos mais alguma coisa. É isso, tivemos aqui esses 4 dias muito... Assim, uma coisa que eu queria comentar, porque vocês vejam só que interessante, porque eu fui perguntado recentemente o seguinte: o que vai ficar depois desse tempo todo de atividade remota? As aulas vão permanecer remotas? Não, não vão permanecer remotas. Eu espero que a gente volte o mais breve possível para um modelo presencial. O que vai permanecer remoto? Esse tipo de evento. Esse tipo de evento. A gente acabou de passar pelo SBQT e todo mundo foi unânime em dizer que foi de excelente qualidade. Esse nosso evento foi de excelente qualidade. Eu tenho a sensação que esse é o modelo que vai continuar. Eu gostaria muito de reencontrar as pessoas, depois, aqui agora à tarde, iríamos sair todos ali para o arretado, e eu ia dizer que encher a cara de cerveja, mas encher a cara de cerveja é falta de elegância. Ia tomar 1 ou 2 cervejas, né, e íamos comemorar. Isso seria o ideal, né? Mas o evento funciona, é barato, enfim, fica gravado. Eu já assisti algumas coisas que eu não tinha assistido, não consegui assistir, eu não consegui perceber exatamente como é que era, já voltei para assistir. Então é tudo de bom, tá? Esperamos que a gente consiga encontrar um meio caminho entre o evento totalmente presencial, que é normalmente muito caro, né? É caro você fazer, e esse evento que nós fizemos aqui agora, que foi feito, por exemplo, SBQT, tá? Eu não sei se alguém quer se manifestar. Não sei se alguém quer se manifestar e falar mais alguma coisa. É isso, Luciano. 2019 nós saímos e fomos ali no arretado tomar uma cerveja. Aqui ninguém é de ferro. O calor voltou aqui em Niterói, né? O calor voltou aqui em Niterói. Muito bem, pessoal. Então, muito obrigado aí pela presença, pela audiência. Eu espero que para todos aqui do laboratório, a gente, a partir do mês de janeiro, não necessariamente todo mundo dentro do laboratório, mas estejamos aos poucos voltando à parte presencial, tá? E vamos nos encontrar em breve. Então, um cordial abraço a todos. Thank you very much for your participation. Goodbye. Goodbye for the Brazilian people. Goodbye for the foreigner. Goodbye for everybody. Tchau, tchau. Obrigado, pessoal da Sua Ciência. Tchau, tchau.